like to thank and acknowledge our sponsors, DC3 Dreams and Voice Astro. DC3 Dreams provides high-end observatory automation and web-based multi-user remote imaging. The AAVSO net observatories use DC3 Dreams ACP Expert for the Bright Star monitors and other programs. The AAVSO Photometric All-Sky Survey Project, also known as APES, has used ACP Expert's AI scheduler to automatically acquire over 500,000 star fields, hands-off, at a rate of 1,000 square degrees per night. This has resulted in photometry for over 128 million objects in about 99% of the sky. The Voice Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals such as the Journal of the AAVSO. Please check out their webpage to learn more about their work. Okay, now ladies and gentlemen, without any further ado, let's get started. Our first of today's speakers is a research astronomer at the NASA Ipec Infrared Science Archive at Caltech, where she's been on the science staff for nearly 20 years now. Her research focuses on the formation of young, low-mass stars and how the rotation of a star might change over the first billion years of its life. Today, she'll be sharing with us some results from the K2 and TESS missions, revealing new insights into some new stars. Ladies and gentlemen, please give a warm welcome to Dr. Luisa Rebull. Dr. Rebull, I'm going to stop sharing my screen and you may now begin.
Okay, awesome. So thanks so much for letting me absorb some of your day today. So yes, I'll be talking about stellar rotation using two different space-based observatories, K2 and TESS. So I'm going to put up the punchline of my talk first. We're going to spend the rest of the talk unpacking what is in this plot. And there's a lot going on in this plot. There's an awful lot going on in this plot. So here what I have is rotation period on stellar rotation period on the y-axis, and then color on the x-axis. So what do I mean by color? Just to remind you, that's what we observe is color is a difference in magnitudes. It's really a flux ratio, if you recall your definition of magnitudes. And as an observer, I'm going to plot color increasing to the right because that sort of makes sense, right? If you have the numbers on your x-axis increasing to the right, that kind of makes sense, except that bluer is hotter, which for the main sequence is also brighter and higher mass. So that means color is mass. Color is a really good proxy for mass, but that means mass increases to the left, which is a little bit brain breaky, but that's how it works. So the high mass stars are on the left. And just to remind you of the spectral sequence, O, B, A, F, G, K, M, L, T, O, B, and A through about the middle of F is high mass stars, and F5 through middle M are low mass stars, and below that we've got brown dwarfs. So what I care about is the low mass stars, right? So I've got maybe a couple things that could be A stars, but mostly I've got Fs through mid Ms in these plots here. And just remember also in terms of the distribution of stars in the galaxy, there's not too many high mass stars, but there's lots more low mass stars. So rotation is one of the three fundamental parameters of a star. If you tell me the mass, the composition, and the angular momentum or the spin rate of the star, I can tell you an awful lot about how that star evolves from its birth all the way through its post-main sequence giant life. And those parameters also have implications for how planets form and migrate in the system. So I know that you guys had at least one, if not more than one, recent ones of these webinars on star formation, but just as a brief review, this is how low mass stars form. We start with a big dark cloud. We're going to zoom in on one of these dense cores, and it's going to start to collapse under its own gravity. And they've drawn the arrows here radially pointing in, and probably initially that probably is what happens. But because of conservation of angular momentum, because that cloud is probably spinning just a little bit, it's big, but so it doesn't take very much, right, to spin just a little bit. And the net result is because angular momentum is conserved, it doesn't continue to fall radially in. It falls onto a disk like a record or a CD of matter before spiraling into the central object. And then, why is it doing that? And then for reasons nobody understands very well, some fraction of that accreting matter turns right around and gets ejected at the magnetic poles of the star. So you get this system where you've got a big thick disk, you've got this cocoon of matter continuing to fall in, then you've got these big jets. Eventually that cocoon of matter thins out either because it's fallen onto the disk or blown away by the jets, and you still have a big disk and jets. Eventually the accretion rate falls off and the disks the jets turn off and the disk starts to form planets. And then eventually you have a genuine bona fide adult star, mortgage paying, hydrogen burning with planets around it, adult star. So if these are the adults, these are the teenagers, and these are the real babies. Okay, but because you heard me talk about angular momentum, particularly in these early stages, but angular momentum also is going to matter through all the rest of these stages. So in the very earliest phases of star formation, the angular momentum is going to affect how the cloud cores fragment into individual stars. And magnetic fields are also going to be important in star formation. For the star and planet formation process, you lose angular momentum because of that interaction between the star and the disk. And the magnetic field is also super important. The star itself is undergoing a radial contraction as it is forming. And so it's also undergoing major structural changes within the star as well. And it could very well be that even during the formation process, a decoupling between the core's rotation and the envelope's rotation matters. On the main sequence, you get spin down, right? Because what happens is you've got winds from these stars. And so even though each individual particle in the wind is just an individual proton or electron, it's getting flung out to very large radii. So if you wait long enough, that's going to slow down. That's carrying angular momentum away from the star. So that's going to slow down the star. And on the main sequence, certainly the coupling between the core and the envelope is going to be important. And then the post-main sequence, after it runs out of hydrogen, the star undergoes major structural changes. The winds kick up, you get more mass loss, and the core envelope coupling becomes important again. So in the very broadest strokes, you're going to start with a relatively large protostar, and you're going to contract. And as it's contracting onto the main sequence, it's going to spin up like a skater pulling in her arms. It's going to spin up. So in the very broadest sense, you're going to start with a big thing and end with a smaller thing. And so everything should be spinning quickly after it's, as it's forming. And as the star lives on the main sequence, when it initially starts burning hydrogen, it's rotating really quickly, which means it has strong magnetic fields, which means it has strong spots and strong winds. And those winds are going to slow down the rotation rate of the star. And eventually it's going to slow all the stars down so that they're going relatively slowly and they have many fewer spots. This only works, of course, for the low mass stars that have a convective outer zone. In the high mass stars, everybody does this, everybody spins up, but the high mass stars don't have this magnetic braking to depend on in most cases, because they don't have magnetic fields. They don't have outer convective zones. And so unless it's a really weird high mass star, this braking doesn't happen in the high mass stars. So in this plot that I started out here, I've got rotation rate of the star as a function of color or mass. And then in the very broadest terms, like if you back up from your screen, you can see there's an overall trend. These guys are going relatively slowly. By the time you reach this clusters in here, you get things that are relatively low in the diagram. They're going as fast as they're going to go. And by the time you get out to the end here, they're slowing down again. So you already know that the story has got to be more complicated than this, because you can see all sorts of structure in these plots. And moreover, I haven't even told you what that red circle means. The red circle means there's an infrared excess. In other words, there's a circumstellar disk around those stars. And so when you have a circumstellar disk, when you add in a disk around the star, it's going to do interesting things to the rotation rate. So here I've got a movie that has a star condensing onto the main sequence. So it's getting smaller, and as it's getting smaller, it's spinning up. And the magnetic field that's visualized in green around it is getting dragged around with it. But when you have a disk around the disk, especially right close to the star, is going to be ionized. In other words, it's going to be charged, it's going to be hot. And so it's going to see the magnetic field. And so even though the star is trying to spin up as it's condensing, it's also dragging the magnetic field through the disk. And the disk says, oh, no, I'm not going to let you go that fast. It's going to grab onto those magnetic field lines and keep the rotation rate slow. So that even though the star is condensing onto the main sequence, you would think it'd be spinning up. But if it has a disk and if it's locked to the disk, then it doesn't spin up at all. It's draining angular momentum through the magnetic field to the disk. So to moreover make it impress upon you how complicated this is, active accretion is almost certainly episodic. It's almost certainly not a slow, steady process in which you dribble matter from the disk onto the star. It probably dumps tons of matter and angular momentum onto the star all at once, and which probably crushes the magnetosphere, which means the place where that magnetic field threads the disk, that locking radius is going to be brought close in, and it's going to puff up the star because you're dumping stuff onto it. And so if you're trying to model it, keeping track of what is star and what is disk and where the angular momentum is going is really, really hard. And on top of all this, these young low mass stars should be completely convective. And if you talk to the theorists, they'll say, oh, well, it's completely convective. That means it's rotating as a solid body, except that maybe it doesn't. The sun rotates differentially, both with latitude. In other words, the equator goes faster than the poles, but there's also differential rotation with radius. And the sun's convective zone does not rotate as a solid body. So we don't fully understand exactly how convective zones work in a rotating star. And in the sun, like I said, the atmosphere, the convective zone rotates differentially, but the radiative zone is supposed to go differentially, but doesn't. And the radiative core does seem to be strongly coupled to the surface convective zone in the sun. But that's really complicated, because when you have that magnetic braking, when you have that winds from the star throwing protons and electrons out to very large radii along the field lines, slowing down at least the outer zone of the star, the magnetic field is thought to be locked to the convective zone. So that means that you can slow down the outer envelope and leave the core rotating quickly. And that idea, at least, is supported by lots of observations, particularly among red giants, because you've got, when the star runs out of hydrogen and it goes into its red giant phase, the star is going to puff up and undergo major structural changes, and it's going to dip into the stuff that had been in the core of the star. In other words, the remnants of burning hydrogen into helium. You're going to mix that into the outer convective zone of the star, and it's going to change the abundances that you see, but it's also going to pull up angular momentum from the core. So it's a puzzle. It certainly seems like the core should be rotating quickly and the atmosphere should be rotating slowly, but the details of that aren't so clear. I'm going to focus on surface rotation rates in the rest of this talk because that's what I can do. But you do see evidence of disk locking and evidence of structural changes in some of the stuff I'm going to show you. So we are really in the fourth wave of rotation studies. The first wave of people studying stellar rotation, they were working with projected rotational velocities. So in astronomers call that V sin I, with photographic plates. So what that means is, if you take a spectrum of a star, you've got the star rotating. One limb of the star is rotating towards you and one is rotating away from you. So you end up with a broadening of the spectral lines that you can measure. And a star that's rotating quickly will have much broader lines than a star that's rotating slowly. So the very first studies of rotation rates of stars were using V sin I's, but with photographic plates. And that got us down to about G0 stars in the nearest clusters. And from those studies, we learned both that high mass stars rotate faster than low mass stars on average, and that lower mass stars spin down with age. The second big wave of rotation studies was again using V sin I, but then with digital detectors like CCDs. So that took us down to mid-M in the nearest young clusters. And it was through that work that we learned that you can have both fast and slow rotators right after the star formation process on the zero age main sequence. We also learned that, remember I keep talking about these wind breaking where you're slowing down, you're carrying matter out along the field lines and slowing the star down that way. Turns out the stronger the faster it rotates, the stronger the field, the stronger the wind, the stronger the breaking it up to a point. There is a point beyond which it doesn't work as well anymore. And that's called saturation, right? Where the wind doesn't break, just stronger wind doesn't break harder after a certain point. And we started to have evidence that there was probably core envelope decoupling. In other words, you could have the core rotating quickly and the envelope slow down. The third big wave of rotation studies was looking at rotation periods from ground imaging. So how do you get rotation periods? When you have the spots rotating into and out of view, you can see the brightness from the star changing as the spot moves across the surface of the star. And so you can figure out what the stellar rotation rate is by looking at the brightness variations from the star. So that got us down to early M in many different clusters and star forming regions. And it opened the field called gyrochronology, which was really, really hoping that if you had a rotation rate, you could figure out an age. Turns out probably is not that simple. We're now in the fourth wave where we're doing this kind of stellar rotation work, the spot modulation rotation work, but now from space imaging. And that has just blown the field wide open. There's been lots of theoretical work on this in the million year, mega year to giga year, billion year timescales. But in order for me as an observer to help constrain the theorists, I need to give them a whole groups of stars of known ages and metallicities, abundances is what I mean, and over a range of masses. And so in order to do that, I'm going to sample clusters over a variety of ages. And up until this point, even for the youngest and closest clusters where the stars are bright because they're relatively close to us, the ground-based data are woefully incomplete, especially for the low mass stars, and very biased because the ground-based accuracies and cadences can only just go for so long. So now, of course, we have legions of people looking for planets, and the really good planet hunters understand that they better understand what the star is doing before they assert what's going on with any planets, because a big planet crossing a star can look like a small star spot crossing the surface of the star. So there's all sorts of wonderful tools out there to do really exquisitely precise photometric measurements. And when you have big spots on the stars, that makes it easy to find the variations due to the stars. So K2 is particularly good for this. What is K2? K2 is the repurposed Kepler mission. So you may recall that Kepler was a planet hunting mission, and it was designed to stare at just one part of the sky. It was supposed to just stare. But in order to stare with the precision that it needs in order to do this kind of high precision work, you need at least 3 gyros. And they lost all but 2 gyros. So that's a problem. Clever engineers figured out how they could make this work. So they could use 2 gyros to control pointing of the telescope in 2 dimensions, but then they can use, believe it or not, the solar wind as the 3rd axis control. Now, the repercussions for this is that the spacecraft is wobbling. It's doing this every 0.245 days. The wind finally pushes it away and the thrusters push it back. So when you're looking for rotation rates, this kind of cyclic behavior from the spacecraft is not ideal, but you know that it's there so that you can avoid it. And still, the machine is spectacular. It can still do spectacularly accurate photometry. But now it can probe ranges of stellar masses and ages that we never thought we were going to get. So when K2 was still operating, it did 70-day campaigns. And because of the fact that they're down to 2 gyros and they were using the solar wind and wobbling and all that, that meant that they could no longer point anywhere they wanted. They could only point in the ecliptic plane, the plane of our solar system. And with a 70-day campaign, you can catch rotation rates up to about 35 days. But most stars rotate faster than 35 days, up to at least 800 million years. So I'm good with that. And K2 had a big field of view. So when the clusters are close, you can catch a lot of them because they attend a large fraction of your field of view. So in order to try to explain what I mean by that, from where I'm sitting right now in Southern California, Boston looks like a point source to me. But if you're in Boston, it subtends a huge fraction of your field of view because you're in it, right? So it's the same sort of thing. When the clusters are close, they cover a huge fraction of the field of view. So when K2, since it had a big field of view, you could catch a huge fraction of the members of these nearby clusters. TESS is, of course, the most recent planet hunter. It has, however, much shorter campaigns than K2. It has much bigger pixels, which means we're limited to just the brighter stars, but it covers almost all the sky. So young nearby moving groups are a really great target because they are bright and they cover huge swaths of sky. And for whatever reasons, a lot of the nearby moving groups we know of are in our southern hemisphere skies, and that's where TESS's initial campaigns were. So now we're back to this plot. We still have rotation period here. So now you know a little bit more about that. I'm going to show you more about that in a minute. We've got V minus A here on the x-axis. And all the periods here are from K2, except for some in this cluster here. The K2 campaigns are 70 days. So that's why my plot only goes up to 35 days. I'm probing lower masses, and I'm able to do this to higher precision than anyone has ever done before. And the additional red circle means that it has a disk. And so its rotation rate is likely to be affected by the disk. So the individual panels here are individual clusters, and you can see they're marked by name, but also by age, so that the list of clusters here is sorted by age. Here's the list of clusters I'm working with. So there's a list of all the clusters. There's the approximate age in million years. There's the number of members that I have, and there's the satellite and reference that the data are coming from. So in the rest of this talk, I'm going to focus on my results. And it turns out that membership is often a huge bottleneck to getting work done. And it used to be that 100 stars of periods was a really big deal. Now it seems rather paltry because we've got clusters with thousands of stars. So it wasn't that long ago that this was state-of-the-art photometry. So what exactly are we looking at here? Let me take a little bit of a brief aside. So in preparation for this talk, I watched several of the recent AAVSO videos that you have on your YouTube stream, and I saw that there were many, many, many questions about phased light curves. So let me take just a couple of minutes to try to explain that a little bit better. So I'll remember how you can think of any kind of cyclical behavior, whether it's like how sine waves are defined or a wheel on a bicycle turning. So this movie it's actually from a geometry lesson in which they're talking about how to define the sine function. So we've got a cycle here. We have something moving around in a circle, and in this case, the projected distance onto the y-axis here is creating the sine wave. Now, because this is cyclical, I could say we're going to start the clock here. Now, a quarter of the way through the cycle, halfway through the cycle, 3/4 of the way through the cycle, back to the beginning. That's phase. In geometry, it's plotted between 0 and 2 pi, but you can plot it between 0 and 1. So when you have, come on, go on the next one. So like I said, in trigonometry, that's plotted between 0 and 2 pi, but if you think of it in terms of fraction of a cycle, that's phase. So you can, for example, start your phase here. That would be a quarter of the way through. That's half the way through. That's 3/4 of the way through. And then you're back to phase of 0. But you can also start the phase clock anytime you want. It's totally legitimate. Phase is 0. Phase equals 0 is an arbitrary spot on the repeated cycle. It's a repeated cyclical pattern. So you can set phase anywhere you want. It can be the first night you started observing your target, right? So if I have a light curve that has a period of 10 days, I can plot it between 0 and 1 phase. A light curve that has a period of 0.3 days, I can also plot that as 0 to 1 phase. If I have a light curve that has 2 periods within it, I can make 2 plots, each of which is 0 to 1 phase. But especially if I have lots of scatter in the light curves, I could also plot it as between phase 0 to 2. In other words, have 2 copies of the light curve to make it easier to see patterns in the light curve. So an evenly sampled, roughly sinusoidal light curve might look like this, in which case when you phase it up, they line up on top of each other. But in astronomy, we have a lot of unevenly sampled data. But that works in our favor when we phase it up, because when we phase it up, we can fill in the gaps. Now here, I've got an evenly sampled light curve, but my star has a period of 1 day, and I'm going to observe it, say, at 9 p.m. every night. no evidence of variability exists in this light curve. So it's impossible to phase it because I don't see any periodicity. So this is why you can't observe at exactly the same phase every time. That was an explicit question in one of the earlier videos. So many of the earliest tools for figuring out what the period is depended on there being really long, unbroken, evenly sampled, high quality measurements, which let's be honest, that's a physicist in the lab, that's not reality. Some medical physics does that too, like an EKG or an EEG also has long, unbroken time series. But the reality of astronomy is that we don't generally have long, unbroken, evenly sampled, high quality measurements because things rise and set, objects move behind the sun and you can't observe them for several months, instrument breaks, weather doesn't cooperate, satellites even orbit and they need to call home to download data. And especially in astronomy, not every point may have the same size errors, especially in like gamma ray and X-ray astronomy, you're counting individual photons. And so it's really complicated. And so astronomers have a huge variety of tools to cope with this unevenly sampled data with weird gaps, varying signal to noise. And you, through AAVSO tools, you have access to some of these tools as well. So we already talked about phased light curves. A Fourier transform, basically you can replicate any light curve by summing up sine waves. But the formal mathematical definition of a Fourier transform needs evenly spaced data, but it's really good at finding periodic sinusoidal things. In the 70s and 80s, two different astronomers figured out how to make Fourier transforms work with unevenly spaced data. And so their names being Lohm and Scargill, this analysis is called a Lohm-Scargill analysis. Finding planets is much more subtle. Finding, characterizing non-periodic things is also hard, and both of those are different talks. When you do a Lohm-Scargill analysis, it gives you something called a power spectrum or a periodogram. Basically, it's telling you how much power or energy, you can sort of think of it that way, as a function of period do you need to recreate the light curve. And this power spectrum can be messy, and you can spend a lot of time deciding where that threshold of believability is. So these were state-of-the-art light curves in the late 90s, early 2000s, and we had 300 targets in Orion and 200 targets in another star-forming region called NGC 2264, and that was a really big deal. Here's brightness as a function of phase, and you can see here there's plotted two phases, right? And you can see that all four of these guys are roughly sinusoidal, and you can see clumping of the data points in here, right? Because with the period of about 10 days, and you're only observing at night, you end up with clumps of data points. Now, I understand that I'm old, you know, get off my lawn, but it was not that long ago that this was state of the art. This is the same kind of analysis, but now from space. So we've got flux as a function of time here. And you don't need lots of fancy math to see there's something cyclical in there. This is the power spectrum. So power as a function of period. Everything, all the power is in that one narrow peak. The texture you might be able to see at the bottom here is not texture in the periodogram. That's the tick marks for the plot, okay? And when you phase it up, it's beautiful. It's a beautiful sinusoid and it's right there. And there's no room to argue. When we were doing this analysis, there was room to argue. We argued a lot about what periods to believe. There is no room to argue here. It is periodic and it's got a period of this fraction of a day. Very few of the stars are not periodic, right? Here we got flux as a function of time and a power spectrum that's just complete crap, especially in comparison to that. So there's nothing periodic here. So for most of the stars that I'm talking about here, it's either periodic or it's not, and there's no room to argue about it. So this was, again, the previous state of the art. Rotation period is a function of V minus K color for the Pleiades, and all the orange points are ground-based periods. And this is what happened after I got to it. If I have a light curve, I probably have at least one period for it. Nearly everything for which I have a light curve has a period. And we're probing much lower in mass. We're reaching into the fully convective stars than we, much lower mass than we ever have before. Here's Praesepe, again, state-of-the-art periods, ground-based periods that were known before. And after I got to it, we're going much lower in mass. And again, these guys are fully convective. So are these samples complete? Well, probably. So here we have just a plot of stuff on the sky, rate ascension and declination. The gray boxes are the individual CCD chips from K2. If it's a green point, it's a member of the Pleiades and I have a light curve for it. If it's red, it's a member of the Pleiades, but I don't have a light curve for it, either because it was completely off the field or it fell in the gaps between the chips. But if I have a period, I mean, if I have a light curve, I probably have a period for it. And so there shouldn't be any bias in my period distribution that comes from position on the sky. I do have a bias in that I'm only going to be picking off the optically brighter stars, which in the Pleiades is, you know, just the higher mass stars. I'm going to miss the later M's. But when we get into some of the younger clusters where there's lots of dust, I'm going to miss the things that are more embedded when I use K2. So especially since you guys love light curves, I have to just share a couple of the spectacular light curves that we got. So this is just a whole collection of these sinusoidal light curves. This is what most of the stars look like. And we interpret that as a big star spot or a group of star spots moving into and out of view as the star rotates. And like 3/4 of the stars are like this, right? They're pretty straightforward, they're sinusoidal, and there's no room to argue about whether or not they're periodic. Then we get guys like this, where there's 2 peaks in the parallelogram. And if you phase up the light curve at the highest peak, that's clearly not right. It's clearly this other peak, which is the rotation rate we need to use. And so our interpretation of this is either 2 spots or spot groups rotating into and out of view. So you get 2 dips for 1 rotation. You get things like this too, where the structures are moving during the campaign. Here's again is flux versus time. And you can see by eye at the beginning of the 70-day observing window, I've got 2 peaks, but that smaller peak sort of moves and merges with the main peak by the end. So if you phase it up at the main peak here, you get something that looks like this. And our best interpretation of what's going on here is that the spots are moving during the campaign, either because we've got 2 different spots at 2 different latitudes, and like the sun, the equator goes faster than the poles, and so you get differential rotation, you measure slightly different periods. Or this could also happen because the spots are evolving, and the spots on the sun certainly evolve, so it stands to reason that star spots would. So either one of those could explain those light curves. Then we get things like this, where you see clear beading in the light curve, even before you do the math. Here's the power spectrum, and you see it's got this main peak, but then this also structure here. This peak is a harmonic of this main peak. So if you phase it up at the main peak, you get this. But what probably is going on here too is that I've got several spots or spot groups, and they're probably measuring latitudinal differential rotation. They're probably spots at different latitudes, and each latitude is going at a slightly different speed. Then you get stuff like this, where you get clear beading, and then you get a power spectrum like this, where if you look really close, there's this shoulder right there. So there's 2 legitimate periods in this light curve, phased, one of them phased here and the other one phased there. So this is an M star with a V minus K of 4. It's definitely an M star. It turns out that almost all the M stars that we find that have multiple periods like this are binaries. So we've got 2 different stars with 2 different spots or spot groups, and we're measuring the rotation modulation from both of them at the same time. And then you get things like this, where you've got 2 pairs of peaks. These are harmonics, these are the main peaks. And they're both real, but I can't imagine a star that has differential rotation that strong. That's probably a binary. It's even though it's an M star, I mean, definitely because it's an M star, it's a binary. But with TESS, we've got bigger pixels, and so you get more source confusion. And so this light curve has a 4-day period and a 0.6-day period. But I don't know if that's a binary or it's just flux from a nearby star that's gotten encompassed in my aperture that I'm measuring the photometry with. We also, of course, have tons of eclipsing binaries. And we've got, in this case, you can see in the original light curve, the dips that are the transits, or the eclipse rather. All of that power spectrum is coming from that dip. And then you've got this other peak that's out here. So if I phase it on the peak power here, that's the eclipse lining up. But if you phase it on this peak, that's the photometric modulation from the spots. So this particular star, there's 2 of them and they're eclipsing, but at least one of them has big spots on it that I can figure out the rotation rate of the star. Then I've got stuff like this, where I have this forest of really short period peaks. That's pulsation. It's pretty awesome. But stellar pulsation is really fascinating, but again, a whole separate talk. Then we get these weirdos. These are really cool. So again, flux is a function of time and 1 strong peak in the parallelogram. And when you phase it up, you've got these weird notches. These notches are too big to be planets and too small and angular to be spots. We have spent a lot of time trying to figure out what these are. As far as we can tell, they are most likely matter entrained in coronal loops. So the corona, the magnetic coronal loops are rotating with the star, and you've got stuff entrained in the loops in these young stars, so that we get much more of these in the younger clusters than the older clusters. Here's a whole zoo of them that we've found in TESS. They're everywhere. And we've broken them into basically 3 categories. These guys we call scallop shells, and they're all rotating really quickly. They're all M stars, and they're all rotating really quickly. Then we get these guys where there seems to be like a continuum in dips. Those can go faster. They can go up to 2 days, but they're often just as fast as the scallop shells. And we've got things like this, where there's a sinusoidal waveform, and then this notch that's taken out of it. And those guys are going slowly by comparison. All of these are M stars. None of them have disks. None of them have infrared excesses, and they're all rotating really quickly. Here's a clue as to what's going on. The shape changes after a flare. So here we've got the black before the flare, the red after the flare. Here's the phased up light curve. You can see the black part here and the red part here. So that part of the light curve, as well as some of those dips, changed after the flare happened. This is on the right, it's just a zoom in on this portion of the light curve. So that's part of how we think, but why we think that this has to do with matter entrained in coronal loops, because it changes after a flare. Here's an example of the transient flux dips. Near the beginning of the campaign, there's a clear angular dip, but by the end of the campaign, it's mostly gone. So in these cases, probably we've got something like an ablating planet or an ablating clump of something that's getting burned, getting blown away by the stellar winds in these young stars. So now for these rotation periods, each one of these points has a fairly reliable period, and we haven't yet explored the stars with disks. Disks can make it harder to find periods because you get the reddening from the circumstellar disk that makes the star fainter, and you get a random contribution from the disk and from the accretion. But you can also see a very clear influence of the disk on variability, and you can actually see evidence of disk locking. So here, these are guys, Flux and the power spectrum here in the phase light curve. You can see there's a sinusoidal component, but then these bursts. This is a burster, and it's their pops of accretion that are happening onto the central star. And then these guys are dippers. You can see there's a sinusoidal component, and then these dips that change every orbit. And that's texture in the disk occulting the view. So just to emphasize, these are called dippers. Some people get confused and call these dippers. These are not dippers. These are disk-free M stars doing other weird and wacky things. These we find all over the late type stars. These guys are accreting, and they all have disks. Both of these guys have disks. These guys are accreting, and this is texture in the disk or the accretion column occulting our view slightly differently every orbit, which is why the dips are different every orbit. So when you have a disk, you can have all the same kinds of variability you have in the stars that don't have disks, but you also get all of this disk enhanced behavior as well. So here I've got evidence that the disk locking is actually working. Here I've got brightness as a function of time. And then here I've got the phased light curve, and the red portion is the contribution we think is just due to the spot. And then on the right, I'm subtracting off that spot contribution, leaving just the dips. And the red hash mark there is the same phase of that red phased light curve. And the dips line up with pretty close with it almost every time. The blue ones are the ones that are out of sync, but the red ones are the ones that are in sync. So this is the first direct evidence that the spot modulated signal is the same as the dipper portion of the signal, which is the first direct evidence that disk locking works. This is the first direct evidence. I've been chasing it for 20 years or more. This is the first direct evidence that disk locking works. So given the large number of stars that I have in Upper SCO, you don't need any sophisticated math. You can just see by eye that in the M stars, there's this pile up of 2 days in the red disk stars. That's disk locking. It's working. So in these earliest clusters, there are not too many stars, and there's lots of disks, and there's lots of reddening. So that complicates exactly where they appear in the x-axis. So on the y-axis, the error bar is very small. The x-axis, there's probably some smearing. So these guys are hard to do. These have a lot of stars, and you can start to see some structure. Here, there's not too much stars. Here, there's a lot of structure. Here, there's some stars, and you can see some structure, and then there's some clear structure in this one where I have a lot of stars again. So like I just said, the error bars are very small in this direction and probably relatively large in this direction, especially for the youngest clusters. Now I'm going to put underneath each one a blue version of the best next most populated one in the sequence. So I've got Upper SCO here in blue and then the row O on top. And you can see, even though there's not very many stars in row O, you can see it's starting to pull out that same pattern. And same for Taurus. And then Upper SCO here, I've got Pleiades underneath. So you can see that this higher mass hook is there. And you can see that that slope is there. Again, these don't have very many stars, but they do seem to line up with the Pleiades. And then the Pleiades here is much different than Hyades or Praesepe. Hyades and Praesepe are essentially twins here. So let's look at just the ones that have the most stars. Here I've got Upper SCO, Pleiades, and Praesepe in black, and then in blue, Pleiades and Praesepe. So there's a lot going on here. Here we've got the Upper SCO higher mass things are not terribly organized yet. We have a clear pileup of disks, but that overall M-star relationship is really steep. By the Pleiades, they're getting much more organized. Here, the disks are debris disks. Here, the disks are primordial disks. So here, they're getting much more organized. And there's some interesting substructure in this arm that suggests we might be seeing differential rotation. And here, we've got this disorganized region. Some of this is due to binaries. Some of this is probably due to disks even. The M-star relationship is steep. It turns out to be the same slope as Upper SCO, just faster because the stars are smaller. And so they're spinning up and conserving angular momentum. But going to the Praesepe, the next step, we've got much more organization throughout this entire structure. This knee right here, this bend, is probably core envelope decoupling because it's easier to slow down if you're only slowing down the outer convective zone, not the whole star. And then you've got this relationship here. You can see it's much steeper than it was in the Pleiades or Upper SCO. And that steep slope also has this funky gap. This gap does not make any sense, but it's there and it's real. So I'm going to skip, just because we don't have a ton of time left, I'm going to skip this particular slide. The newest data that I've been working on is from TESS. And because, like I mentioned, TESS covers a huge fraction of the sky, you can catch some of these nearby associations much more easily. So this is a huge map. It's like 80 degrees corner to corner. There's Upper SCO here. That's the gaps there are the K2 gaps. And Upper SCO is probably part of the same moving group, the same association as Upper Centaurus-Lupus and Lower Centaurus-Crux. It turns out to be both an age and a distance gradient across these clusters. But so the distance is between 100, 150 parsecs for all of these guys, and the ages are between 10 and 20 million years, but Upper SCO is closer and younger than these guys. And you can see, so everything that's magenta here, I have a K2 light curve and a period. Everything that is yellow here, I have a TESS light curve and a period. And these funky gaps are a result of TESS's observing strategy. So there's like 3,000 stars in UCL and LCC, and it's taken me a lot longer than I anticipated to go through this collection of data. But let's see how it fits in. This is still preliminary analysis, but you can see that it sort of does fit in the sequence here. You can see that we've got, here I've got Upper SCO, now UCL and LCC, and then Pleiades. And then the Pleiades is in blue underneath. So you can see that this higher mass thing is starting to get itself organized. This slope is probably the same between Upper SCO, UCL and LCC, and the Pleiades. It's just that UCL and LCC are a little bit older than Upper SCO and not as old as the Pleiades. And that 2-day pileup is still there. Even though I'm working with a totally different set of stars and totally different telescope and totally different biases, the 2-day pileup is still there, which just makes me really, really happy. So there's my summary slide. I think I'm ending more or less on time. And with all of the main points of the stuff I was talking about here, but now you understand there's a rotation period versus color as a proxy for mass. And you can see how the relationship, the rotation rate changes with time and mass across all of these clusters. So I'll take any questions that you guys have.
Okay, thank you, Dr. Rebull. All right, let's see. We have a currently 5 questions in the Q&A box, and people are welcome to continue submitting as we're answering. Let's see. First one from Michael Poxon asking, if the disk download process is so episodic, why do we not observe more FU Orionis stars?
So the FU Ori stars, just to make sure that everyone is on the same page. So when you have, come on, where did my slide go? Okay, so when you have a disk around a star, the way that it's drawn here, the magnetic axis and the rotation axis are parallel, right? And so that probably doesn't happen exactly very often. Probably the magnetic axis can sometimes be inclined. And so even under standard disk locking, you can get, because you see this gap, the magnetic field truncates the disk before it gets all the way into the star. The matter that's in the inner disk will actually crawl up the field lines and crash down onto the star. And especially when you have a magnetic axis that's not quite the same, is inclined with respect to the rotation axis, at certain parts of the disk, it's easier to crawl up, to crawl up the field lines and crash onto the star than others. And so you get some episodic behavior from that, but probably our best understanding is that you end up with the magnetic field acting as some kind of a gate, right? Some kind of a magnetic gate that blocks the accretion. And so when you end up with the magnetic gate continuing to accrete matter, eventually it catastrophically accretes onto the star in one horrific episode. And FU Orionis stars are that, right? So FU Orionis, the definition is it starts relatively faint, gets brighter all of a sudden, and then never really fades away. So remember that stars' lifetimes are very, very long compared to ours. So FU Orionis are relatively rare because the stars take a long time to do that, and that huge, huge dump of matter and angular momentum on the star happens relatively rarely, although people are looking for it. Certainly less catastrophic accretion happens all the time. You don't have to just be an FU Ori. You can, there's a variety of flavors of other large variable stars where they start faint and get much brighter, and then on 20-year timescales they start to fade off. So those are probably lesser versions of FU Orionis accretion events. And then there are other less dramatic but still episodic ways of dumping the matter onto the stars. And so we're starting to understand the timescales for all of that kind of behavior because we have all of the time variability data sets now. And so that is really the edge of the envelope of our understanding is the time, the cadence expected for all of these various kind of episodic accretion events.
Thank you. Great answer. Okay, Michael Poxon has asked, any likelihood of performing similar analyses on Herbig AEBE stars in associations or MGs?
So that's an interesting puzzle. So in order for us to get the rotation rate, we need to be able to have spots on the star. So in order to have spots on the star, our best understanding is that you need an outer convective zone. So Herbig AEBEs are already well on their way to the main sequence, and so they're not completely convective anymore. And so they might have magnetic fields, but the topology, we're not entirely sure. Is it dipolar? Is it something more complicated? How many spots do you expect? So it's complicated. And in order to get the rotation rate, you need spots. And so if you don't have spots, then you can't get the rotation rate. You can't do the same kind of analysis. People do look at projected rotational velocity. They do look at V sin I's. And a lot of the high mass stars rotate quickly for a very long time. And that's part of how we know that the spots are related to the outer convective zone. So the short answer is no, there's no easy way to do it because the higher mass stars don't have the spots.
Thank you. We have another question here that says, I'm curious how planetary ingestion events via the eccentric Kosai-Lidov mechanism impacts the rotation profile of young clusters. This mechanism has been shown to occur during initial 100 million years of a cluster.
Yeah, so it's an additional variable, isn't it? It's, so in reality, it's complicated. I didn't even mention planet ingestion. Planet ingestion probably matters a lot in the red giant phase too, because our own sun is going to end up with a radius that encompasses all the planets up to and maybe including Jupiter. So yeah, planet ingestion is going to make a big difference, probably in terms of giants, in terms of the abundances that you measure. And there's a whole collection of red giants that are going much faster than they should. And so one of the proposed resolutions to that observation is that they've eaten a planet. And so the ones that are going too fast, people look for abundance anomalies as well as rotation to go with the rotation. And it turns out that some of them also have an infrared excess, which could come from dust produced in the red giant atmosphere, but it could also be debris from a shredded planet. So yeah, it's a puzzle. And certainly the planet ingestion is going to affect the rotation rate of stars at any phase.
Very interesting. Thank you. All right. Zhen Guo has asked, for the UCL/LLC region, is there any substructure or population within the region, given that it's such a huge area?
So there's lots of people that have done studies looking for differences among these. Upper SCO seems to be a different, significantly different than UCL and LCC. There's definitely a distance gradient. There's definitely an age gradient. The details of it are only recently emerging. I haven't, in terms of other properties, right? Like proper motions, and net space motions and things like that. People are trying to separate out these two associations with Gaia data. The source list that I started from was assembled using Gaia DR2. And then I am literally in the middle of doing this analysis. So this is still very much preliminary work, and I haven't had a chance to break it down in finer bins. Like I could, at the very least, break it down in bins of galactic longitude, but I haven't had a chance yet because 3,600 stars is a lot to pull through. And so it's taking me longer than I anticipated to write up this work. But so that, yes, that's something definitely I'll be interested in delving into. The additional complication is that because of the big pixels, there's a lot of these stars that probably I'm not 100% sure that I'm measuring the rotation rate of the star I think I am. And so that's the big thing I'm fighting with now, is sorting out those kinds of source confusion issues. And when I get rid of the sources that I'm worried about there being source confusion, I may end up with too few stars to break them up into finer bins. We'll see. Like I said, I'm right in the middle of doing this analysis, so I don't know yet.
Thank you. We have a couple other questions here that are more like comments, but might be informational to the attendees, so I'm going to read them out. If you have any comments you'd like to add, please do so. So John Merle said, I am using the shortest length of string method implemented in a spreadsheet to find the phase curves for eclipsing binary stars in the Gaia data, and it works surprisingly well, probably because Gaia photometry appears to have very low errors.
Yep, and the eclipsing binary is a really obvious signal. So it makes it easy to find, because most of what I'm studying, most of the rotation rates are sinusoidal. I can quote unquote get away with just the Loam-Scargill. I don't have to use a lot of these other methods. But you see the eclipsing binaries, they have a very angular notch, right? And so the Loam-Scargill is kind of struggling because it's trying to make a sinusoid match up with a small angular notch, which is why you get all of these harmonics, right? So especially for eclipsing binaries, yeah, you're right. Loam-Scargill may not be the best way to do it. And your method or some of the other methods that are available in the AAVSO software may be a better choice than Loam-Scargill for the case of eclipsing binaries.
Thank you. And one last comment in here was also from John Merle, who had initially asked what the units of the rotation rate and the K2 rotation rate plots were. And then at some point in the presentation, it was revealed that that scale is days. So
yeah, I just was trying to unpack it little by little. Sorry.
And I think we have time to take this. One more question just came in from Neil Miller, who asks, have you considered Gaussian processes to deal with quasi-periodic signals?
Yes, but again, since most of the overwhelming majority of my sources are happy sinusoids, I don't have to. That's when I first started and I was anticipating light curves like this, I figured I was going to have to do a whole suite of different period finding routines to decide what I liked best. And most of them turn out to be really easy to do just with Loam-Scargill. So I don't have to fuss with additional methods because the Loam-Scargill gives me what I need in most cases pretty straightforwardly.
Thank you. Looks like that's it for questions. So thank you,
Okay.
Dr. Rebull. All right, our next speaker is a researcher at the Harvard-Smithsonian Center for Astrophysics. She might seem familiar to y'all as she gave an excellent presentation on our Aquarii and some other symbiotic stars during an AAVSO webinar last August. She's quite the expert on the subject, having spent many years studying LPVs across the wavelength spectrum. A key part of the success of her studies has been AAVSO observations, from the long-term monitoring of LPVs in general to targeted observing campaigns for specific objects. Today, she'll be sharing with us some recent exciting results that AAVSO observations have contributed to and outlining the potential for AAVSO observers to help with future discoveries. Ladies and gentlemen, please give a warm welcome to Dr. Margarita Karovska. Dr. Karovska, feel free to turn on your screen share and your video.
I have my video. Start your video because the host has stopped it. So
Okay,
so
it should be in the lower left corner of your Zoom window.
Yeah,
there should be a...
I am clicking on it and doesn't let me.
Oh,
because it was stopped by the host. So
I apologize. Let me see if I can do something about that. There you go. Can you do it now?
Yep, start my video.
Sorry about that.
There I am. By the way, is that cartoon for me? Is that me on the picture?
Yeah.
Thank you. I'll have to match. Okay. Hello, everyone. There is my screen, share screen. Where did I get that one? Okay, there is my share screen and the view slideshow. There it is. Can you see it? Hello?
Yes, ma'am.
Can you see it nicely?
Yep, it looks great.
Okay, wonderful. So, hello, everyone. I am I am very grateful for the invitation to speak of some of my favorite objects in the entire universe, the long period variables. And I'm very grateful. Also, I would like to thank to all the observers, the director of AAVSO, Stella Kafka, the members of the headquarters, all of you who have helped me over the years tremendously by enabling to do the research, exciting research that I've been so lucky and blessed to do. So, long period variables. I took a nice graph first from Wikipedia showing the main sequence star, Hertzsprung-Russell diagram, and the place where many of the LPVs live. They are old evolved, some of them, old evolved supergiants and giants, sometimes having a companion stars. They are cool, cold, and they are in a stage of life where they're kind of approaching the endpoints of their evolution, which might be explosions at type of as a supernova, or forming planetary nebula, or ending up as white dwarfs, or neutron stars, or black holes. These stars show variability on many scales, as the AAVSO light curves show. The variations we can see on time scales from days to months to years, even centuries. And the database that AAVSO and other light curve databases have shown is extremely valuable for studying the long-term behavior of these exciting stars. I myself, I have a pet name, is stellar geriatrics, because they are in their older stages of their life, and connecting to the previous talk, they do remember their youth, but the youth is not so recent for them. The AAVSO long-term monitoring LPV light curves, long period variable light curves, show sometimes regular periodic brightness variations, which are due to pulsation in some cases, like Myra's few magnitudes of changes within few hundred days. Long secondary periods of the order of 1,000 days have been observed in these stars. But also many of them show irregular or semi-regular variation or on short and long time scales. A number of LPVs are in binary systems. Some of them have swallowed their binary companions, some of them still has them, and some of them have companions that are compact objects like white dwarfs, accreting mass from the powerful wind of given cool giant, AGB star, or supergiants. Often they are so close that they form a symbiotic systems, which I mentioned in my August webinar, and I also will talk today about. They are fascinating sources. And although they look regular in their behavior in the light curves, I have seen many incredible surprises and over the years that I've been studying them, and as shown in the light curves of LPVs. So in this talk, I will highlight some results from multi-mission, multi-wavelength, high angular resolution observations, with emphasis on a critical role that AAVSO long-term LPV observing plays in monitoring that had enabled many discoveries, not just for me, but number of people, and the potential for the future discoveries. A lot of information is there at the AAVSO web pages. And here is a screenshot of LPV section web page, which is just beautiful, very detailed. And I will suggest that people take a look if they haven't already. Also, that web page gives a lot of information of why observe LPVs, how to observe LPVs, which they are, LPV of the month, and so on. That is truly, truly very helpful. In this talk, I will give a bit biased, maybe more than a bit biased, personal view of LPVs, which is based on my decades of research of these objects using multi-wavelength techniques in symbiosis with long-term monitoring and campaigns by AAVSO and spectroscopic observations done, for example, by ARA's group. I fell in love with the long period variables when I was a undergrad student, got acquainted with the AAVSO and the light curves. And then I did my thesis in Nice, France, on the high angular resolution observations of one of the most beautiful stars for me on the sky, which is Betelgeuse. Now, before I go and highlight a few of the objects that I personally have observed or I have interest continuing observing, I would like to mention that the nearby supergiants and giants AGB stars are indeed unique laboratories for studying variability and underlying physical processes. We are talking pulsation, stellar structures, convection elements, spots, sporadic outbursts, even jets, on spatial scale reaching close to the circumstellar or circumbinary environment. and even resolving the stellar surface features. These studies required multi-wavelength observations with maximum sub-arc second resolution, and I named several of the telescopes, including SPACE and GrandPACE, that can be used, and many of those are not here on the page because they will fill the page and pages if I would write them all. Using key information on the variability of these sources, including light curves and spectroscopy, many of exciting results have been obtained this over years. So starting with the Betelgeuse, the alpha or in the Orion constellation, I will say few words about the ability to resolve these stars. About 100 years ago, this star was resolved by Michelson and Pease with an interferometer. And for the first time, the diameter of the star was measured. It wasn't possible to image it. The imaging came later in the 70s with the spectral interferometry and interferometry in general, which I was participant in the observations that allowed obtaining the first images of the stellar surface and the surrounding region. That was part also of my PhD thesis. Betelgeuse is at a distance of about 150 parsecs. It's a red supergiant. Mass, let's call it 15 solar masses. It is massive. Radius, several hundred solar radii. I put here a value of 700, but it's still something that is being measured. When we say radius, we think of the photosphere, but this star has been defined by a colleague of mine many years ago, White, as a jellyfish, because in addition to the photosphere, there is extended tenuous atmosphere. It's very similar with Myra, which I'll be talking later. So other than the spectral imaging of the structures on the star that has been done by several groups in the past, in the mid-90s, the star was imaged and resolved by Gilliard and Dupree using the Hubble Space Telescope. It's a 40-50 milliarc second star, so it's small. You know, it's really hard to resolve it and image it, but definitely it's not symmetric, and probably is showing that there are some kind of structures on the star, probably related to the supergranular structures, convective structures that are waxing and waning on the star as proposed by Carl Schwarzschild in 1975. This is an optical image. It has been observed also with the VLA. This is a 7 millimeter image. The black circle in the center, my pointer doesn't work very well, but the black circle in the center is the photosphere, and the VLA observation showed the extended tenuous atmosphere, molecules and gas, molecules and dust. If you look at the image to the right, that is a image from the very large telescope in infrared, 2 instruments we used. And the photosphere itself, it is in the center of that black circle, which is the field of view of one of the instruments. And you can see the incredible animated atmosphere or dust envelope shells that are surrounding this star. More recently, Betelgeuse was resolved by ALMA, and it shows definitely that the structures are not, the structure is not uniform on the star. The disk is not uniform. The size is, as shown here in the press release, almost the size of Saturn, the extended atmosphere, if you put Betelgeuse in the center of our sun, but definitely something that looks either maybe spots, either supergranular material, supergranular structures on the surface of the star. The resolution is insufficient to decide what it is. If I had, this is a simulation by Freitag, and he has done several over the years, including recently, of what the supergranular structures will look on the star. These are connected to this deep convection structure in the interior of the star. If you look at that, because of the lack of resolution, this same image may appear like what we see on the left, when the resolution that we have is not sufficient to see sharply the individual structures. I can come back after the talk, if anybody is interested, say a little bit more about this and also about what my dream is. Alpha Orionis, it's regular, semi-regular, and unpredictable. This is the 90 years light curve shown here on the AAVSO web page, 10 days mean. And I don't know why can I use the pointer, but that is a bit a problem. There it is, it's showing. Can you see the pointer?
Yes,
I think
we can see it.
So you can see that it's anything but regular. However, in the 80s, and including part of my thesis, and later on, we have discovered a regular 400 days period in this irregular looking light curve, plus longer periods, about 6 years, and maybe even longer, 20 years, which it's maybe semi-regular on the longer scales. But also we have discovered that there are occasions like what you see in 1926, in the 40s, in the 80s, where there is dimming in the star, which has been interpreted by people as episodic mass ejection, formation of dust that is dimming or obscuring the photosphere of the star. The recent dimming, or they call it the great dimming of Betelgeuse, it's truly exciting. As you can see in this light curve, AAVSO light curve, the star behaved till somewhere in late 2019, where the light started dropping pretty fast within a month, a couple of months, and then went down for almost a magnitude, 0.8 magnitude. Went to a minimum and then quickly came back, and still now we are waiting to see what it's going to do, but I think it's clear that it's out of this deep minimum. The great recent dimming of the star. Many observations were carried out during this period and are still being carried out in optical, light curves, spectroscopy, imaging, multi-mission, and still are being carried out now. So we'll see what the story comes out of it. Even looking on the sky, you will see, or you could see that there is a difference for what it used to be. I usually myself, I compare it with Rigel. I was taught, that's one thing you can do also with Aldebaran. And I'll tell you, I have looked at Betelgeuse for many decades. And when I looked during this time on the sky, it was very disconcerting for me. It was like, this is just not right. It's not exactly like if the sun had disappeared, but it was quite interesting, the reaction that I had, but it shows before the dimming and after the dimming. The star has been followed, as I said, by a number of techniques, observatories from space and from ground, number of observations. And here we have 2 images of the star within a year apart, from January 1919 to January 2019 to December 2019. These images obtained with very large telescope square instrument on ESO by Montager et al. And you can see the difference. You can see the difference. Is this a supergranular spot, a supergranular? Because as Schroeder predicts, there will be only few at the time of the surface. Or is this supergranular, or a spot that we don't have enough resolution to see what it is, that it's changing, rotating, moving, or is it perhaps absorption? Or there was an ejection of material likely, and formation of dust that it's absorbing, maybe the photosphere and the close stellar environment of Betelgeuse. This is an artistic, from the press release, artistic view of what it might have happened. But we can just infer, but we cannot for sure say for sure that that's what it was. As I mentioned before, this is the same light curve. This dimmings in the light curve has occurred in the past. My dear friend and mentor, Leo Goldberg, had published a paper on the variability of Alpha Orionis and had brought 4 occasions where this had happened. He had studied, he had combined the observations of the radial velocity and the light curve and of Betelgeuse, and had found that when there were occasions of low radial velocity, the radial velocity dipping for several, in this case, almost dozen kilometers per second. Following that, there is, when it brightens, there is a follow-up dip in, or dimming in the light curve. This is observations of stabbings during that time, and this is the AAVSO light curve. So it shows you how important it is to observe, not to say, oh, well, we know what it does, but to keep watch for episodes like that. He is describing one in 1926, in the 40s, and then late 80s in his paper. And this is what he says: as the pulsating star reaches maximum velocity of expansion and begins to decelerate, there may be instabilities set up in the atmosphere which trigger mass ejection and the formation of dust grains. So the paper was written in 1984. It inspired another part of my thesis where I did period analysis for Betelgeuse, but what it inspired also interpretation of the interferometric images that we got and allowed to explain what was happening. The images were gotten a couple of years later, and it showed the central, the photosphere of the star, that's the radius, and then shells, newly formed shells, scattered light from dust shells, that was the interpretation, within a couple of radius close to the star. The next star that I'll say a few words about is Antares, or the neglected twin of Betelgeuse, or I'd call it the close cousin of Betelgeuse that we need to pay more attention to, because it's a fascinating supergiant at about same distance as Betelgeuse. It does have a companion at about 3 arc seconds distance from the giant, which is about 500 astronomical units. It's a B star. It's not a small star, if 7 solar masses compared to Antares, when maybe 15, 11, 20, but let's say 15 solar masses, and similar size to Betelgeuse. They are completely detached as far as we know, because they're quite distant from each other. So Antares is, we can observe Antares as also a single supergiant. This is the AAVSO light curve of Alpha SCO Antares. And you can see in this light curve that it's not as well covered as Betelgeuse. We do have episodes of sharp dimming that is very likely, in my mind, connected to episodic mass loss, due perhaps to combination of the appearance, waxing and waning of these supergranular structures, rotation and pulsation of the star, but is still unknown for sure. Just as a plea to the observers to, if at all possible, please observe in visible, visually, and in V and other wavelengths, B, as much as you can, Antares, and cover more of its light curve. This shows the last 70 years of the light curve. And hopefully we get something like what we have for Betelgeuse as the time progresses, and identify these very important events that we can trigger observations like we did for Betelgeuse at the Great Dimming. Antares was also resolved 100 years ago with the Ps, with Michelson Ps and the interferometer that I used. The diameter was measured. It's also about, compared in milliarc seconds to Betelgeuse. But recently, it was resolved with a very large telescope interferometer in infrared. On the left, this is from their press release, is a press release. On the left, you see the image that they have obtained by reconstructing using the visibility maps from this very large telescope interferometer. And again, there is a structure on the surface, possibly as rendered in this artistic view spots, or are they spots? Or is it something else? Are they supergranular? What is it? We need more observations, and we need to see how it's changing with time. These stars are very important, this supergiant, because they are potential progenitors of core collapse supernova type 2, as is shown here with Kosai and others. So understanding what's going on with the progenitors, what is causing these instabilities, and how is their mass loss going, because these stars lose a lot of mass during their aging lifetime. It's key to understanding how it gets from here to there. How do they get from here to there? We need more supergiants, and that I can address later on in my dream. If you ask me what my dream is for these stars. Another star that it's much less massive, it's about 1.5 solar masses, 1.2. It's Mira, the prototype of Mira variable stars. It's about 100 parsecs distance. It does have a companion, very likely a white dwarf, or 0.6 solar masses, and is separated about twice the distance between Sun and Saturn, about 70 to 80 astronomical units, or only 0.5 arc seconds on the sky. Mira AB, you see here in the center, is surrounded by a tremendously interesting emission from regions with dust, molecules, maybe associated, and gas, maybe associated with previous outbursts an increased mass ejection from the system. This is an ALMA image, but Ramstad did all 2014. Mira itself is a pulsating AGB star. The star pulsates with a period of 332 days. It's quite repetitive, and it's shown in this Porter et al. Simulation of the star. You have structures on the star that are also due to this convective underlying envelope of the star, and it's showing as these supergranular structures on the star. Schwarzschild predicted that for AGB or Mira type star, we could have a few dozen to 100 of these supergranular cells. Dozen of them, like shown here, will be very interesting to resolve. So they are more numerous than for supergiants, but we don't know. We really need high resolution observations of this systems of these stars, and especially when they're in binary systems. In case of Mira, we have the regular periodicity as shown this AAVSO light curve, shows the visual and visible and blue, B, and R, and other filters. It shows pretty regular observations, but take a look at the maxima. They're not at all the same. Sometimes they're bigger, sometimes they're smaller, brighter, fainter. And then the recent light curve shows also these bumps here. We've seen them before, but this is something going on with the star. This is not negligible. Thanks to AAVSO light curves. I mean, I'm very focused on this region here, on these observations. They still persist in the new cycle here. And we should try to get as many observations as we can and figure out what it is. The spectroscopist, the ARAS group, is on it. And we need to really follow up and look for these events in the long-term light curve, let's say on Mira and other Miras. The other thing is, as I said, Mira has a companion, and the companion is most of the time not visible, is dominated by the bright A star, the Mira, which changes within 332 days, but close to 7 magnitudes. But at the minimum of the star, from time to time, the companion is peeking through the minimum. And we see it. And we've seen it in International Ultraviolet Explorer spectra. People have seen it optically in BE. And it's interesting, itself is variable by 2 magnitudes. The companion actually, we believe it's a white dwarf surrounded by a accretion disk mimicking a B star. So it's very interesting. Why is it varying? And indeed, do we have this period of 14-somewhat years in the brightness of this source? In 1983, we observed Mira with the Steward Observatory 2-meter telescope and resolve it at about 0.55 arc-second, resolve the system. There is Mira, there is B. By the way, as in Kelvin in Hobbes, you people who have fun, you like their cartoons. Oh, the world was black and white at that time, including the Astrophysical Journal and other journals' images. So what you see here is a black and white image of what we saw using speckle interferometry. The important thing to notice in this image is that Mira itself, Mira A, is not round, is elongated. That was the first time that the asymmetry in Mira A was detected directly with speckle images. Number of observations have followed from the ground, and then including in 1995 with the Hubble Space Telescope. The asymmetry changes in direction, and here it is, where we see it in this deconvolved image of the Hubble Space Telescope reaching the maximum resolution that one can do with this beautiful space telescope. The asymmetry is there. Is it spots? Is it supergranular? Is it a non-radial pulsation? This is persistent. It had been seen by other people in other Miras. Miras are symmetric. What is causing this asymmetry? Are they connected to the sequence D in the LMC observations of light period of the luminosity period observations by Wood et al.? We don't know yet for sure, and it's worth continuing exploring. Mira is a binary, and although it's separated by 70 astronomical units, 70, 80 astronomical units, is supposed to be detached. In this picture, we say Mira A and Mira B. Before the deconvolution, you saw the deconvolved image on Mira A, but then Mira B, the convolved image showed a little hinge pointing to the Mira A. Now, in these detached systems, it was believed that there is no direct exchange of matter. The companion, the white dwarf, or the compact companion, is accreting matter of the powerful wind coming from the giant, from the AGB stars, and forming an accretion disk. Bondi-Howell theory predicts that only 1% of mass is accreting on this compact object. However, the observation of 995 and then another observations that came later, including with HST and Chandra, showed that even in this detached system, which are accreting from the wind from the mass-losing star, there is exchange of matter, not via Roche lobe overflow, but via a focused wind accretion where the companion is accreting from the tenuous atmosphere and the wind of the mass-losing star. In this image that was obtained in 2005 with Chandra, not only we can see the bridge between the stars, but the big surprise was that the observations were to see the companion. AAVSO was critical for the success of these observations because we wanted to observe when Mira is not visible in the minimum, so we don't have any leak of optical life or anything overwhelming. Mira showed emitting in X-rays, totally unexpected. Totally unexpected. So much, for they are predictable and know what is happening. Follow-up observations a couple of months later with HST showed the bridge as well and showed that there was an outburst or maybe even a jet-like type of ejection of material in Mira A. And you can see here in this artistic view where not directly related to Mira, but showing, the accretion. But we also did with my former students and colleague, Miguel de Valbora, and a group of people, we did hydrodynamic simulations, 2D and 3D, showing that because of the tenuous atmosphere of Mira A, it is possible to make the material flow toward the companion, even when there is no outburst through focused wind accretion. And the amount of material accreted is of the order of magnitude higher than predicted of Bondi-Howell. This was unexpected. It's very important because, I will show you a couple of other symbiotic stars where ability to accrete on the white dwarf is critical, because some of them are having a companion that is 1.1, 1.3 solar masses. So if you dump enough material on it, it would be able maybe to go as a supernova type 1a, and it's probably responsible for some of the supernova type 1a. I gave the webinar on symbiotics, and here I will quickly go through two, this was in August, through two LPVs that I'm working on, and they're absolutely fascinating. One of them is Sirseg. It was used as a standard star, red star, in the beginning, I would say even 40 years of the last century. And then around mid-40s, something started happening and became more and more pronounced in the star, showing, till this is around beginning of the 70s, clear periodicity, which is still there, of about 100 days. So, and in the spectra, it started showing itself as a symbiotic with an accreting companion, a blue spectrum superposed on the red giant star spectrum. The giant is about 2 solar masses, and the white dwarf can be 0.7 solar masses, 0.6. We don't know for sure. Mid-70s, look at it. Look at what happened. This nicely behaving star. Look at what happened. There was an outburst, and then the system has never been the same. One thing I'd like to point out, after the outburst, there was this deep drop in brightness, better shown in this graph. And Taylor, Swift, and Mattei, Taylor and the group, and Janet Mattei observed it in radio and detected a jet that was formed soon after this big dimming of the star in radio. In addition to this one, there are several others that have been observed, and maybe even a recent one now. In 1996, my dear colleague, Janet Mattei, called me and said, guess what is going down? That is the region here. Did call the director of VLA, and we got observations soon after, within a year, detected a radio jet that was expanding following this dimming, was probably associated with mass ejection from the system and a formation of the jet. I will just focus on this region here. This is 2006, where another big dimming happened. So trained by Janet about what these events, what to look in the AAVSO light curve, here we were ready. We applied for HST time, and not just HST, Chandra, and also VLA time. And in 2008, and then later on in 2012, we obtained gorgeous observations of the Sirseg system, which I will show you here. So this is the reconstructed image using the convolution techniques. You see the size 1 arcsecond is shown here. The binary is somewhere in the center. It shows a jet and a counter jet and a region around the binary, plus a very strong bright blob at about 2.5 arcseconds from the center, that when you saw the image in X-ray, I couldn't tell it was as bright as a central image region, never seen before. So the green is Hubble Space Telescope observation in the optical. The red is Chandra, soft X-rays, and the blue is the VLA observations in radio. The material is moving from the spectra that were taken around that time with a velocity over 1,000 kilometers per second. So it's a fascinating object. to show how the resolution really matters. This was an image, the SS of CH Cygni on the sky, and the little square here, when expanded, this is what we saw in a high angular resolution. And this jet is processing and showing incredible changes. This red spot here, enhancement of emission in X-rays, so it's probably the jet shocking pre-existing shells, dust shells around this fascinating system. And one more irregular system, I showed that one before. It's a Mira star. That is the now brightest star in the system with a white dwarf. The separation between components is 15 astronomical units, and it's one of the closest symbiotic systems, about 200 parsecs away. You can see the binary somewhere here in the center. There is a tremendous amount of material on that. This is like 30 arc minutes around from previous major outbursts and mass ejection in the system. But you can see it's also dominated this beautiful jet coming out from the binary, probably collimated by the region close to the accretion disk. It is a Mira with large amplitude, and it's varying with about 390 days period. About 40-some years ago, there was a fading that was observed, Wilson and all, and was interpreted as a periastrum passage of the white dwarf component, white, and the accretion disk being affected by the material dump on it, but also the material dump in the system, making another powerful jet be ejecting at that time. I will just, if I may have just a few more minutes on this. So here it is, we are now 2017, 2018, June 2018. I come back from vacation from Europe and I check my favorite LPVs. And I look at our aquarium and say, well, something is wrong. I have to call. I mean, 2 magnitude absorption, 2 magnitudes absorption. Something is going on here. The periastrum, the next periastrum was predicted 2022. It started early. And matter was ejected somewhere here, and we see dimming of the light curve in several filters, but this is visible and be presented here. The minimum reached almost 13 magnitudes in V, just incredible. So it's similar now, it's getting toward the minimum now in March. But here, I'll tell you, in the last a bit more than a year, spend a lot of time applying for time and getting time and observing with my colleagues, especially during the minimum with space and ground-based observatories, monitoring, asking for campaigns, which I'm very grateful to AAVSO and ARIS for observing optically, the light curve optically and other wavelengths, and also for getting spectra during this time. See, the Mira is faint. This allows me to see what is happening close to the Mira and close to the system, because in the images, for example, from Space Telescope, it's not overwhelmed by the bright Mira. And it's acting like a coronagraph of the region close to the binary. And this is what we got. You've seen this image, perhaps, if you watched the previous webinar. But we see the binary is in the center. This is 0.4 arc seconds. We are reaching in the HST and under observations to less than 10 of an arc second resolution. in the central region, which is exposed here. We see the jet, we see the jet and the counterjet, and we see the ionization cone. The green is the oxygen 2 line. We see the high energy in blue in X-rays, and in red, we are seeing the soft X-rays. It's incredible amount of beautiful data which we got. Thank you for this alert from the AAVSO light curves. And we're analyzing and working on a couple of papers, at least a couple of papers on the results from this. Why they are important? If you put enough material on the white dwarf, you know, they will go as supernova type 1a, at least we think. They are also progenitors of a symmetric planetary nebula, at least fraction of them. They are called they're called nanoquasars, because if I look in the image here, and I did not tell some of my colleagues in the group that I work on Seyfert's active galactic nuclear, they wouldn't know from the morphology that this is a stellar system. The difference is in scale and the velocities. In the AGN, the velocities go to a fraction of the speed of light. And here, it's few thousand kilometers per second, and in one of the massive white dwarf symbiotic binaries, like Arctic Crew and MWC 560, which is also stars that we're observing, and very grateful for the AAVSO campaigns. We have velocities that have been measured to 6,000 kilometers per second. So they are very interesting to study because they are progenitors, at least of a fraction of supernova type 1a, distant scaling indicators, and planetary nebula. So they are fascinating systems. And so I put now the conclusions. The seemingly regular behavior of many LPVs, anything but that, when studied on time scales of years. The long-term photometric monitoring of LPVs is crucial for understanding the physical characteristic processes, including of evolution of these stars. We saw how important the multi-wavelength high-resolution observations are in symbiosis with the observing the light curves in spectroscopy and other techniques. And we showed that even detached binaries like symbiotic systems show focus wind accretion. And so the studies of mass loss characteristic are so important, and the structure on the stars, because they're key inputs on the stars in the surrounding region, because they're key inputs to evolutionary models and models of progenitor or supernova type 1, 2. And so why is it important to observe and monitor LPVs? Because their behavior is fascinating, unexpected, and surprising. And that has been my experience with observing several members of this group over several last decades. And each time I thought, now it's done, now we know. It was not the same as before. Something happened, and I'm still fascinated with these wonderful, incredible objects. So I'm giving the pointer again to the AAVSO webpage on LPVs, and with gratitude, I would like to finish this part of the talk. So.
Thank you, Dr. Karovska. All right, are you ready to start taking some questions?
Yes, please.
Okay, looks like we've got 6 so far. The first one comes from Patrick Kavanaugh, who would like to know, why are there gaps on the graph for the AAVSO observations of Beetlejuice?
Beetlejuice, in general, it's not all the time observable. It goes behind the sun, unfortunately. So it's true for Myra, it's true for many of the LPV stars. So they can be filled. They're the one that I maybe filled better, but always there are the gaps, and they do affect, as it was mentioned before, they do affect the period analysis. And since you see that this dimming is pretty sharp, you can miss it if it happens, or you can miss part, or you can easily miss when it hits the bottom, if it is during the period when it's not observable. I would say, our aquarium, we just got VLA observations. We have HST observations planned for May and Chandra for April. It's going behind the sun. Please take as many observations, photometric and spectroscopic, as you still can before we go into the gap, because the observations that we are planning will be in the gap, or some of it.
Thank you. We have a question here from Richard Roberts, who has asked, is CH Cygni a triple system?
Yeah, has been brought up in the past, has been brought up by Hinkle and other, that there may be a third companion, that it's a giant. At this point, we are not sure. I'm presenting it as the binary because we can see the effect, and I'm more interested in the symbiotic part, which seems to be the closed binary. But the question is still open on that one, although many people are considering as a binary now.
Thank you. Another one from Richard Roberts. He's asked, are CH Cygni's jets persistent or intermittent?
The observations that we have had over years show that both. It's very interesting. The observations of 2008, 2012 show that the inner jet is precessing, seem to be there all the time. I think it's similar to our aquarium. But then you have these sporadic outbursts of blobs being thrown out in the jet. And we definitely see in our observations the outer jet basically changing in brightness, in position and brightness as well, as it interacts with the surrounding regions. So intermittent, yes, because we do see sporadic ejections, more matter thrown out. But as persistent, yes, because the inner jet is there, and we are seeing it in our observations, especially HST observations that we've carried over years. And we are working on a paper.
All right.
Coming soon.
Thank you. We have a question here from Zhen Guo, who said, first, great talk.
Thank you.
He says, on the recent dimming of our aquarium, comparing with previous years, why did the amplitude also shrink by about a magnitude? And did the jet also change the pulsation scale of the AGB star?
The pulsation scale, as you've seen in the light curve there, I can go back just quickly, is the same. You see, it seemed to be keeping the 390 period. It's same here now. But what you see here is absorption, is tremendous absorption by 2 magnitudes. It looks like a cloud of dust that has formed because of ejection of material and dust formation that is absorbing in the maximum, in the minimum, very likely the Mira star, and maybe both, the binary as well. So we see in the observations that were done during this period, we see also formation of a new jet ejection or a parcel going out of the system, which we are following now, that therefore the observations that are planned, that just happen in VLA and happening hopefully in the next couple of months. So this is absorption. It's not a change in the amplitude. It's like if you put here something that it's absorbing severely, the material, the light coming from the Mira and a likely companion.
Okay, thank you. Good explanation. Okay, so Constantino Sigismondi, I apologize if I mispronounced your name, has asked, what can be the shortest time scale of magnitude variation on Beetlejuice, for example, of 1/10 of a magnitude?
Hi, one of the collaborators and somebody who had worked very, very diligently on the recent Beetlejuice behavior or misbehavior. And so hi, Constantino. For Beetlejuice, I would expect that there will be changes. I don't know whether, of the size that you're talking about, but I would expect that there may be changes even in weeks or months, depending what one observes. Will be interesting getting some high-speed photometry as well. As I beg that it's done also for the other symbiotics and for Myra when they are at the minimum. So I expect variation on all kinds of scales. I hope that answers the question.
Sounds like a good answer to me. All right, so we had another question from Richard Roberts, who had asked, can a symbiotic trigger a type 1a supernova explosion?
No, that's the $1 billion question, right? One of the reasons why I myself and others are fascinated by these object symbiotics is because they are potential progenitors, or at least a fraction of supernova type 1a. And this will be in the single degenerate so-called scenario, where you have the white dwarf accreting from a red giant, and then the white dwarf goes kaboom when it gets enough mass, 1.4 solar masses or so, the Chandrasekhar limit. Whether they are or not, we want to learn, and we want to study their progenitors, or the ones that are especially close in mass, the more massive one. And one of them is that I work personally on is RT-Crew and MWC 560. MW 560 had shown velocities reaching 6,000 kilometers per second at the outburst. I mean, that's not something to neglect. I mean, it's not exactly relativistic, but it's not slow per second. So so they might be. So that's one of the things that it takes my interest. And of course, there is debate between the single degenerate and double degenerate group of people saying that, no, it has to be two white dwarfs colliding, or, there are different variants of the scenario of single degenerate and so on. But it's to be seen. So we need to observe it. We need to observe and find more of these interesting things happening in the stars and follow up for multi-wavelength, multi-mission observations. And my thing is high res. As you've seen, there were a lot of images here. I am a bit biased in that way. So potentially is the answer.
Okay, thank you. Franz Joseph Humpsch has asked, has our query been showing such a recent or such a dimming in recent time?
Our query?
Yes.
Yeah, it happened as I was showing the light curve in 2019-20, and it's still going on as we speak now. So yeah, now it is possible as well when it's at the minimum, and now in March will be at the minimum. It's already kind of low that we are seeing actually its companion.
I see some
at the minimum, and maybe some oscillations as well. So we're not sure, but yeah, we are.
I see some clarifying comments coming in from Franz Joseph. I think he was asking about in the past, not the current dimming, but has it shown these kind of dimmings before?
Yes, about 40 years ago, 40 somewhat years ago, a dimming like this occurred, not as well covered as now, but dimming occurred at that time. and was interpreted, as I said, Leon Wilson and others, was interpreted as a periastrum passage and formation of absorbing dust cloud that was absorbing the light, at least from the Mira star. So it's happened maybe a bit early from the orbit by Gromitsky and Mikhailowska predicted, but hey, it's very hard to get the orbit correct, and it's spectacular that we're even close to it, and we are seeing another periastrum. Now, for some of us that are younger, we can wait 40 years, 44 years for another one. But I myself, I'm very excited now, and the observations that we are getting, and that is just happening now when we have all these observatories, ground-based in space, and all the observations, and all the CCDs, and all the AAVSOers and people who are doing spectroscopy that are able to observe it.
Yes, it is very exciting.
And hopefully they'll observe in 40 years.
Yes.
40-some years.
Okay, so on the topic of our query, we have a question from Michael Poxon, who has asked if our query has also had periods of reduced variation.
In a sense of reduced variation for its pulsation period, or reduced variation with these events where you have less, where something is happening to the star. If it is reduced variations, is the previous question, yes. And also like Myra, I mean, take a look at the maxima and minima and the AAVSO curve. It is not a image. Each cycle is not an exact image of the previous one or the follow-up. So, yes.
Michael has submitted a clarifying comment that he was asking specifically about a reduction in amplitude. So
yes, definitely 40-somewhat years ago, definitely was very similar to what we are seeing now.
Okay, thank you. We have a question here from Scott Donnell, which I'm also interested in the answer to. He asks, do long period variables show variations in their spectral features? And should amateur spectroscopy focus on the entire spectrum or just some particular spectral lines?
Definitely. The answer is yes, definitely. For all these observations, recent ones, one we have called on AAVSO, and thank you, and I talked with Stella and Elizabeth and other people at the headquarters. When the call for campaigns came, we also asked for spectroscopy. And I've gotten some wonderful spectra from the ARAS group and others at the maximum and the minimum. Since the observations that we are doing, I'm speaking about myself and my group, we are focused at the minimum of the star because we are after the jet, after the accreting companion, and after whatever is happening now, and we don't want Myra really covering everything so you can see the companion or the jet forming region and so on. So since we are observing in a minimum, for me, it's very important to get the spectra, and I've been getting spectra not only for our query for CSIG, but also for MWC 560 and RT-CRU. These are the recent campaigns. And of course, you want to have at the maxima, and that's where the Myra itself is dominating. And there are spectral changes between maxima and minima in the Myra itself, as seen in, many of the Myras, but including in Omicron Ceti, Myra, and as I said, other Myras. And we followed, for example, in the UV and magnesium 2 lines. And in optical, there are tremendous changes in the H alpha, in the Balmer lines, whether it's bright or whether it's at maximum or whether it's minimum. So the answer is yes. Please follow as much as you can. And light curves and spectroscopy are key.
Thank you. All right, and we have a question here from Michael Poxon, who says that our query and etc. that you have been talking about are all M stars. And do we see any similar things happening with, for example, carbon stars?
In my research, I have focused on oxygen-rich stars. It just happened that way. I am sure, you know, the carbon stars, you have even more mass lost and more, it should be similar, but I myself, I have not studied. I'm looking at the closed symbiotic stars, or the closed oxygen Miras and giants, but symbiotic stars that I'm able to resolve with and so these are just highlights of the work that I'm doing, but yeah, yep.
All right, thank you. And we have one last question here. It's from Richard Roberts, and he says, please share your dream.
Thank you, Richard. Are you the only one, Constantino, listening to the, no, I'm just, no. So I share my dream. Well, first, I mentioned that we don't know. Well, I will show you here what happens if you don't have enough resolution, insufficient resolution. These are some models. This is by Freytag of, let's say, Betelgeuse, and this is by Porter of a Mira type star. When you have a telescope, let's say 2.5 meters, like a space telescope, in optical, the resolution is wavelength dependent, right? Mm-hmm. So let's say in the optical, this is what it's going to look. This was done through simulation, through CSIM, for a mission that I will show just in a minute. And here it is what we have seen, this is Antares, for example. Mm-hmm. But is it this? Is it this? We need more resolution. Now, if I had a telescope with 500 meters diameter, I could see these structures like that. This is the model. This is what I will see for Betelgeuse. Move to 2 kiloparsecs from the 150 parsecs that it is. Stars like Betelgeuse. How many giants will be able to observe if we had this? Now, putting a telescope with 500 diameter in space, it's not easy. The lower panel shows what we'll see if we have smaller telescopes, right? Therefore, the stellar image. This was selected as a vision mission a number of years ago, and it's actually individual telescopes, each 1 meter of diameter, but arranged in a special way that they are separated, maximum separation of 500 meters between them. And so when the image comes into the hub and transmitted to the Earth, you can see details on Betelgeuse-like stars at 2 kiloparsecs. You can see structure on a solar type stars. These are the plages or the active regions that are nearby our sun. We can study the activity, right? And you know, maybe we can get some beautiful image like this from a symbiotic star. Also, we can resolve the inner regions, broad emission line regions in AGN, for example, quasars. So a lot of opportunities. This is a free flyer, but recently we got a study completed for a stellar imager on the moon in the southern lunar crater. So my dream, this is my dream, that this will happen. And you know, we are hoping in the 30s, and we are trying to propose and get first the moon with the Artemis missions, and then later on a free flyer. And distant future dream. So just to mention, the increase of the resolution between current telescopes, like Hubble and interferometers, will be an order of magnitude. Here is 2 orders of magnitude, but of the interferometers, an order of magnitude. And if you compare to Galileo's telescope, you can see how much jump from the Hubble telescope to a stellar imager telescope will be compared to the jump between Galileo and Hubble. And the distant future dream, this is a beautiful painting by Chesley Bonestell of Man on Myra. In the book Man of Myra, which I recommend to read, and you can see Myra in the background seen from a hypothetical planet. The white thing here is the white dwarf surrounded by the accretion disk. So I hope at one point we will be able to discover planets around these objects, but also that somebody in the future will get this type of view. So, a dream.
Wow, that's really cool. Thank you. Thanks for sharing. All right. So it looks like we don't have any more questions. We do have some messages coming in saying thank you for a crystal clear and informative presentation. And I would like to second that.
Thank you.
A huge thanks both to you, Dr. Karovska, and to Dr. Rebull for sharing your time with us today.
Thank you, AAVSO and associates. Thank you.
Yeah, thank you.
Thanks. All right, I'm going to go ahead and close your screen share and put up the end card if you don't mind. There we go. All right, now before we end the webinar, I would like to thank again our sponsors, DC3 Dreams and Voice Astro. DC3 Dreams provides high-end observatory automation and web-based multi-user remote imaging. The AAVSO net observatories use DC3 Dreams ACP Expert for the Bright Star monitors and other programs. The AAVSO Photometric All-Sky Survey Project, also known as APAS, has used ACP Expert's AI scheduler to automatically acquire over 500,000 star fields hands-off at a rate of 1,000 square degrees per night. This has resulted in photometry for over 128 million objects in about 99% of the sky. The Voice Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Today's webinar has been recorded, and the recording will be made available for free on the AAVSO's YouTube channel, where you can find a full library of recordings just like these. Go check it out, and while you're there, consider subscribing to our channel. Not only will you get notified every time a new webinar is posted, but by hitting that little subscribe button, you'll be increasing our educational reach and making YouTube more likely to suggest our videos to others. It's just one more way that you can help support the AAVSO. Speaking of support, this webinar series is being supported by you, the viewer. So please, if you're not a member, join the AAVSO. AAVSO membership comes with a whole slew of benefits, including free access to our mentorship program. If you're wanting to become an observer and maybe look at some cool LPVs, and you're not sure where to start, our mentors can absolutely help you hit the ground running. If you are already an AAVSO member, don't forget to renew your membership. And of course, we would be grateful if you would consider donating to the AAVSO. Every donation matters, and it goes towards making programs like this come to life. One last thing before you go. After you leave the webinar, you will be automatically directed to a survey. Please do fill it out, even if you've already filled it out before, because we want to hear your feedback. This is a great chance to make some suggestions and let us know what you want to see in future webinars. Do note, the survey is anonymous, so if you use it to ask any questions that you want to receive a direct reply from the AAVSO about, make sure that you write down your email address in the text box at the bottom so that we know who to send our reply to. Finally, I would like to extend one last huge thank you to both Dr. Rebull and Dr. Karovska from all of us at the AAVSO. We appreciate you.